So by this point, we know what the Poisson process looks like. That's the visual below me. And we know some of the behavior of it. It's a counting function, this staircase type of a looking path, which goes up by 1 each time. So it's kind of counting different events that are occurring, and the lengths of these little steps are exponentially distributed, and the parameter with which the parameter of that exponential distribution determines the rate of the Poisson process. So if n is a Poisson process of rate mu, so not necessarily a standard Poisson process, in which case mu would be 1, then this increment here, which is best thought of as the number of events during this time interval. So if you just pretend on the drawing there, if you put in some time s and t, if you look in between those two and you count up how many times the Poisson process jumped, that's the count of events that happened between these two time endpoints. The distribution of the increment is going to be, not surprisingly, as we know, Poisson random variable, and the parameter of it is going to be equal to mu times the time length of the increment. So mu times t minus s is the parameter of the Poisson distribution involved in the increment, and now we can go ahead and compute various expectations of interest. So suppose, in a degree of generality here, we want to compute the expected value of f of the increment. So this is a function f. It takes in a number, a natural number, and spits out a real number. And we're looking at the expected value of f of the increment. Well, that's just going to be a sum over all the possibilities. The possibilities are f0, f1, f2, f3, and so on, times the probability of that happening, which we know from all of the arguments earlier. So let's look at a few basic examples. What's the expected value of the number of events in the time interval s to t, right? The expected value of the increment. This is a pretty simple calculation, but all you need to do is just stack up all the possible values against the distribution. So it's n is the possible value of the increment times the distribution, which is right here. And now there's a few kind of tricks. First of all, the n gets canceled, giving you an n minus 1 factorial. That's simple. And the trick is we kind of have to get to the point where this sum looks like something we know how to compute. So let's take out the rate of the parameter of the distribution, namely mu times t minus s, and things simplify. And this sum, if you really think about it, is very easy to compute. In fact, it's the sum over the probability distribution of the increment. If you look at the starting point here is n equals 1. The reason for that is in this step here from line 1 to line 2, I've ignored the value n equals 0 because for n equals 0, the inside, the term that we're summing is 0, so we can ignore it. That's the other thing that happened from line 1 to line 2, is that we switched the sum to run from n equals 1 to n equals infinity. And now, after taking out a bunch of, after canceling out the n and taking out the parameter, we have the following expression where if you start substituting, the value 1, 2, 3, and so on, you'll see that this sum is the same thing as summing up this distribution from n equals 0, 1, 2, 3, and so on. Right, I'm subtracting a 1 everywhere, and I'm starting at 1. That's the same thing as summing up the original distribution over 0, 1, 2, 3, and so on. So this sum is just, converges to 1. It has to, because that's the definition of a probability distribution. All the probabilities summed over all possible values have to sum to 1. So this ugly summation goes away, leaving 1 mu t minus s, and that is in fact the expected value of the increment. We can do very similar things for the variance The variance would involve two calculations. One of them is the expected value of the increment squared, which we already know. So the variance of nt minus ns is just the second moment minus the expected value squared. We already know the expected value from the previous slide. That was mu times t minus s. Square it. And now the only relevant part of the computation is this one. And very similar tricks involved. I'll let you kind of pause the video and look through this. In a sense, all I'm trying to do is arrange things, right? Manipulate things by taking out certain values and rearranging the sum in a certain way to kind of get the things that I know how to compute. And so what I've arrived at here is I've managed to extract the 1 from this larger sum and have the remainder term be a sum that I know how to compute. In fact, I've written this inner term in these parentheses as 1 plus the sum that will look exactly like the expected value of the increment leaving this term. So if you follow this computation through, this is the final answer that you get for the variance, and the summary of this is that if you want a prediction for the Poisson process increment, that the best prediction that you have is the expected value, namely the number of events between time s and t is going to be mu times t minus s, the expected value. That's the best prediction. With an uncertainty, that is the standard deviation, which is computed as the square root of the variance, so plus or minus the square root of mu times t minus s. So that's another computation of that type. Here is a more interesting computation, which looks at the covariance or autocovariance function. The autocovariance function is right here. It's the covariance between the process with itself at different points in time. And the main ingredient has to be this expected value of the Poisson process times itself at a different time point. And the reason this is key is because this part we've already done before. We know what the expected value of the Poisson process is. Each one of those is an increment, one going from 0 to t, and the other one going from 0 to s. So these two here will lead to this term being subtracted, and what we really are after is this calculation here. So let's look at how we run that. So we start off with expected value of nt times ns, and one useful trick that we used for this similar type of calculation in the context of the Brownian motion was the independence of increments property. So I'm trying to exploit independence of increments, and so I'm going to add an ns and subtract an ns. So in other words, I haven't really changed anything, but what it allows me to do from line 1 to line 2 is to use linearity of expectation. That's how I get this term. And the second is I'm going to use independence of increments, because here what I have is the product of two increments. Right? I've written it out even more carefully. You just write out ns as the increment from 0 to s, and those two are independent, leading to the product of the expectations, which we know how to calculate, coming up here, right? So I've used the independence of increments, and in the meantime, you can follow along here. I've dealt with the second moment separately. The second moment is just the variance plus the expected value squared, and those things we've done already. We've already computed the variance, we've already computed the expectation. The variance is mu s, the variance of ns is mu s. The expected value of ns squared is mu s squared plus s squared, and the product of these two increments give us just mu times ts. That's this term right here. That's the expected value of that increment, times mu s times s, which is the expected value of this increment. And so you get this, and things simplify a little bit, and you have this mu squared ts plus mu s as the expression for this expectation. And then the final thing you really want to get to is the covariance function, which we now plug in. This part right here comes from the expected value of nt times ns, and the subtraction comes from this term, which we know how to compute. The final result is a simple enough formula, us, and you can see that the role of t and s could be interchanged. We've assumed here that s was less than t, and we had to do so in order to line up our increments in this way. So t had to be larger than s, otherwise these would not be increments here. But the role of t and s can easily be interchanged, and so if you were to flip things around and said that t was less than s, then the answer here would be mu times t. And so here's the general formula for the covariance, the autocovariance function of the Poisson process. It takes its parameter mu and multiplies it by the minimum of the two times involved. And this is, again, maybe not surprisingly, given that both processes come from a random walk, very reminiscent of the Brownian motion, where if you run that calculation, and I think we have, you would get the volatility squared times the minimum of t and s. Okay, so what's next? We could look at conditional distributions. So, this is an unconditional distribution for the increment. We can try to look at the conditional distribution of the increment. So nt minus ns is equal to n, provided that we already collected these many events. Well, the condition here is not going to do very much for us. The increments are independent, and so what we're calculating the probability of is independent of what we're conditioning on, and therefore the conditioning doesn't affect the result, and so we get again the unconditional probability from the previous step. If you want to kind of argue for this rigorously, this is a property of the conditional expectation, wherein you take these probabilities, write them as conditional expectations, and the property that you use is exactly that of the conditional probability. When you condition on a random variable, which in here it's this indicator, that's independent of the thing that you're evaluating the conditional expectation of, the conditioning doesn't do anything. And so that's just a slightly more rigorous way to write down this argument. And where we are going to see conditioning play a role is in this transition probability. And I call it a transition probability because we're transitioning from being in state k at time s to being in state n at time t. So we've counted n minus k events from time s to time t. And this is fairly simple calculation. It really helps that the Poisson process is integer valued, so it's a discrete random variable at any point in time. And so we can apply these definitions for the conditional expectation. The two events, probability of A conditioned on B is just the probability of the two jointly considered divided by the probability of the conditioning set. And then from here on, it's just a little bit of manipulation. What I'm trying to do in the second line, going from here to here, is just to exploit the independence property again, so I can kind of take care of this numerator. And so what I've done is I've subtracted ns from both sides, and that's done right there. And because ns is given as the value k, I arrive at at a pretty simple computation. One of them looks at the probability of two increments considered jointly together, but because they're independent, they will split up in the next step. Right? So from here to here, this is again independence of increments, really useful. You then cancel out this term and you arrive at a pretty simple answer, which is quite intuitive. We've said that this conditional probability should be the probability of getting n minus k events, given that we start at k and end up at n. Well, that's the same thing as having the increment accrue n minus k events. Right? In other words, given k events by time s, getting n events by time t is the same as getting n minus k events during the time interval involved. So the formula seems fairly reasonable. The next thing we could look at and should look at is the property of time homogeneity, which is a result of all of the computations that we've done so far. So one thing that we've just shown a second ago is that the conditional transition probability from having k events over to n events is the same thing as the increment accounting for the difference, and that's Poisson distributed. Right? We know what the distribution is for the increment, so we can happily write this psi down. You have to require that n is greater than k in this case, because the process only goes up. And the next thing you note is that if you actually try to come up with the probability that the Poisson process at time t minus s is equal to the same difference, you'll get the same exact distribution. We know what the distribution is for the Poisson process at any value at any time. So in particular, we can try time t minus s, and if you just plug it in, you'll see that both of these maybe surprisingly match. And what that's explained by is the time homogeneity property of the Poisson process. And what the time homogeneity property implies is the following thing, right here. So what it's saying is that regardless of where you start your process at, so here it started at time s with k time units, and we arrive at time t with n events counted. This is exactly the same as starting at time 0 with 0 events counted and accruing n minus k events in the same time length, t minus s. So in other words, the starting point of the process doesn't, the starting time of the process doesn't matter. You can start at time s and wait for n minus k events to occur, or you can start, as this side here says, start at time 0 and wait for the same length of time, namely t minus s, and the distribution of getting those required n minus k events doesn't change. Right? So we can restart the process anywhere, and the distribution of the number of events remains the same, provided you give the same amount of time for those events to be accumulated. So that's the time homogeneity property of the Poisson process. It should remind you of time homogeneous Markov chains, which could be restarted at time 0, and they would evolve according to the same probability law, as long as you give it sort of the same amount of time for the dynamics to take place. The same thing is true for the Poisson process now in continuous time. Final thing I'm going to do here is look at a slightly awkward calculation just to show you a couple of tricks. Let's say we reverse time and we say, what is the probability that in the past we had k events, given that in the future we had n of them? So here we're thinking of n being larger than k, of course, and we're thinking of the time s being before time t. And so what is the probability that we had k units of k events at time s, given that by time t we've accumulated n such events? And here, again, the calculations are kind of the same. It helps that everything is discrete valued. We can write down the conditional probability very easily. And the next trick is just about reversing the order. We were put in a position where time was kind of reversed. Well, let's reverse it back again to something we know. So this the numerator here, the joint distribution, can be written as a conditional probability that's ordered in time in the way that we're accustomed to. So S in the past being in the conditioning, and t being in the, what's actually being computed as a probability, times this extra factor which comes out of the definition of, which comes out of the conditioning. So we started out by conditioning on the future. We've rewritten things where in this step we're conditioning on the past, just like we like it. We've already ran that computation before. It was just equal to the probability of the increment accruing the number of required events, which is n minus k. That's how you get to the next step. And then if you kind of simplify things a little bit, here at this point I'm going to use just the straightforward definitions of what the distribution is for the increment t nt minus ns, for the increment ns minus s0, and the increment nt minus n0. And when you plug everything in, plug in those Poisson distributions in and cancel out, you get something that is actually binomial with parameters n and s over t. So this is an interesting thing to think through. I'll encourage you to do it kind of on your own. Look up what the binomial distribution is. It has to do with kind of arranging events with a certain probability, so a certain number of events with a certain number of probability, and the formula is actually quite sensible. You have kind of n minus k events that you have to arrange, and you have a certain time interval in which you have to arrange them in from time s to t, and so there's sort of a ratio, the s minus t ratio that comes up there is really coming from the fact that there are two intervals involved, from 0 to s and from s to t, or sorry, from 0 to s and from 0 to t, and the fraction sort of, their fractional kind of length of each is s over t. So the interval from 0 to s occupies a fraction s over t of the interval from 0 to t. And so now you just have to, in this formula, distribute the leftover n minus k events in those two intervals. And so that goes a long way in explaining this binomial distribution that arises from this time reversal in the conditioning. Okay, next up is the martingale property, but that's all for this clip.